Using trig functions of 30 degrees, find the values. Okay. The reason Mr. Schwartz is saying use 30 degrees is because what are we studying? We're studying double angle. And what happens when you double 30 degrees? 30 degrees plus 30 degrees, that's doubling it. That gives us our 60 degrees. So we could say what these are right off, but we're not going to. We are studying double angles. We're going to use double angles. So that's how we're going to get to it. We're going to use our double angle identities. So let's just get, you probably have a unit circle right there. That's good. You can always use that. Here's 30 degrees. Whoop, come on. 30 degrees. 1, 2 for the hypotenuse. Okay. So we know that the sine of 30 degrees, the sine of 30 degrees is 1 over 2. The cosine of 30 degrees is the square root of 3 over 2. And the tangent of 30 degrees is sine over cosine, or 1 over the square root of 3. All right, so what's the sine of 60 then? A sine of 60 is going to be, we're going to use our single theta, which is, I should write that down. Theta, our single theta is 30 degrees, right? Half of double. 2 times the sine of single theta times the cosine of single theta. So I've got 1 over 2, the square root of 3 over 2. So 2 times 1/2 is 1. So I end up with the square root of 3 over 2 for this one. Cosine of 60 degrees. Now, I've got a negative here. You start with cosine and then you subtract sine. Cosine squared, subtract sine squared. So this one is going to be cosine squared, square root of 3 over 2 squared, minus sine of single theta squared. So I get 3 over 4 minus 1 over 4 equals 2 over 4 equals 1/2. Makes perfect sense. And then the tangent of 60 degrees, I'm going to say, is the sine of 60 degrees over the cosine of 60 degrees. So sine of double angle is the tangent of double angle is the sine of double angle, square root of 3 over 2, divided by the cosine of double angle, 1 over 2, which simplifies to the square root of 3. So there they are. Example 2. If we know that the sine of A is 4/5, okay, so we know that sine is positive. We're told that this is in the first quadrant. So what does that mean for cosine? Well, cosine must be positive too. Everything's positive in the first quadrant. So I can figure out what cosine is, can't I? If the sine is 4 over 5, that's y over r. This is a 3, 4, 5 triangle. So I've got a y equals 4, an r equals 5, and the x then must equal 3. So my cosine of angle A, the single angle, is 3 over 5. And I know the sine, it's in quadrant 1, so it's positive. Figuring out my double angle is going to be 2 times the value of single angle sine and single angle cosine. This turns out to be 12 times 2, 24 over 25. Okay, and let me just erase this for a minute. So I see over here we're going to be figuring out what quadrant the double angle is in. I know that my double angle, 2 theta, at least the sine is either here or here, right? Because it's positive. Then I have the cosine of the double angle, and I have learned by now that I take the cosine of the single angle, square it, and subtract the sine of the single angle. The sine of the single angle is 4/5. The cosine of the single angle, so I get 9 over 25 minus 16 over 25, which gives me a negative, right? The larger one is negative, so negative, what is it? Difference between 9 and 16, 7, that's right. I should box these. Okay, so now I know that cosine is negative for this. It's positive here and here, and negative here, so I know now that I'm in quadrant 2. What does that tell me about tangent of the double angle? It's also going to be negative. I'm going to use the simple way and say the tangent of this is equal to the sine of the double angle, so I'm not even worrying about the single angle, cosine so what will this be? It'll be 24 over 7, and it'll be negative. And we know we are in the second quadrant. All right. Double angle formulas. We're doing more here. Given that the tangent is negative, all right, so it's positive here and here, therefore it is negative here and here. Tangent is negative. A is in quadrant, oh, they tell us. A is in quadrant 2. Find the values of 2A. All right. I think I have memorized thank goodness. This will be 2 times the sine of the single, well, I better figure out what the sine of the single angle is. Okay. The sine of A, well, in the second quadrant, It's going to be positive. I know what x is. X equals 3. And y equals 2. Where does the negative go? Well, if I'm in the second quadrant, my y is positive, my x is negative, so I've got to say this is a negative 3. And r, which is always positive, what does that equal to? I'm going to square this, which will give me 9, and then I'm going to add the square of this, which is 4. That'll give me 13. So r is the square root of 13. So sine is going to be 2 over square root of 13. Cosine, a single angle, is going to be negative 3 over the square root of 13. So it's negative, which I know anyway, if it's over here, it's got to be negative. 3 over the square root of 13. I'm going to use these two. My sine, 2 over the square root of 13 times negative 3 over the square root of 13. What does that become? 2 times 2 times negative 3 is negative 12. Square root of 13 times square root of 13 is 13. All right. So for 2a, the double angle, I know that my sine is negative. Sine is positive here and here, so I must be either in the third or fourth quadrant. In a moment, I'll know which. Cosine of the double angle, I take the cosine of the single angle and square it. I take the sine of the single angle, square it, and subtract it from cosine single angle squared. All right. Cosine is negative 3 over, that's a negative 3 over the square root of 13. And this sine is 2 over the square root of 13. I know when I square negative, it's going to become positive. I'll have 9 over 13 minus 4 over 13. So it's going to be positive, and it's 5 over 13. So cosine is positive here and here. So that tells me I am in quadrant 4. When I go to do tangent of the double angle, I'm not going back to the single angle values. I'm going to use my sine of double angle, cosine of double angle, and it'll be, in this quadrant, it'll be negative, and it shows that it's negative anyway. It's going to be negative 12 over positive 5. There's my sine of the double angle, and the quadrant I'm in is 4. Express sine of, oh, this is such a great problem. 4x. So we're going to think about it this way. Sine of 2 times 2x. which is equal to 2 sine 2x cosine 2x, right? And then we're going to go from, let's see, so if we have sine of 2x, I'm going to do little bits and pieces now. I'm just going to work on this piece right now. It's 2 sine of x cosine of x. True? So I could start rewriting this. I could say, we'll put it down here, the sine of 4x equals 2 times the sine of 2x, which is 2 the sine of x cosine of x. And the cosine of 2x, cosine of 2x, if I were to keep it all in sine, it'd be 1 minus sine squared x. 1 minus 2 sine squared x. So let's go back to green. This one. Cosine 2x equals, what do we say again? 1 minus 2 sine squared. 1 minus 2 sine squared, sine squared x. So now I'll write that into my new formula here. 1 minus 2 sine squared x. So there I have it. I've expressed the sine of 4x in terms of the angle x. So I had to do a two-step process here. Well, isn't that neat? I think that is so neat. Now we could probably simplify this even further, but I'm not going to take it any further in the interest of time. I am, however, going to do both of these. We're going to verify these two identities, and we're going to work with this side. I've got, let's see, the sine of x. Now notice over here where I'm trying to get to is a single angle. So I have to get rid of this double angle. We know the sine of 2x is equal to, in terms of a single x, 2 times the sine of x, the cosine of x. And what happens here? I've got sine of x over sine of x, which is equal to 1. So I end up with 1 over 2 cosine of x, which could be written as 1/2 of 1 over the cosine of single angle x, which could be written as, yes. How about this one? Well, let's work with this side. We'll end up verifying to here. Does that look like anything we know? Sine x minus cosine x squared? Not really. I mean, the first thing I'm thinking of is the Pythagorean identities, but those have both of these squared, not squaring on the outside. So I'm just going to go ahead and FOIL this. That's, of course, sine x minus cosine x times sine x minus cosine x. I'm going to FOIL it. And when I do, I get sine squared x, and that's my first, and then I get my outside, then I get my inside, and then I get my last. My outside is going to be a negative sine x times cosine x. My inside is going to be a negative sine x times cosine x. So it's going to be a negative 2 sine x cosine x. That's my outside and inside. Oops, and that's an x. And so I've done this, I've done this. The only one left for me to do is right here. Negative times a negative will be positive, so I'll have a plus cosine squared x. Ooh, I love it when that happens, because this plus this is the Pythagorean identity, and it's equal to 1. So that's 1 minus 2 sine x cosine x. And we know that that's an identity. Yeah. What is that equal to? We've been working with it a lot. 1 minus sine 2x. There it is. Now for a little fun here with using an identity to evaluate an expression like this. And one of the things you notice right off is we've got arctan, which means that we're talking about an angle here. And what is that angle? It's the angle at which tangent is 3/4. X is 4. Y is 3. So we're here. And what else do we know? We have to figure out what R is, but we can see that this is a 3, 4, 5 triangle. So it's double the angle which has these relationships. Okay, so that tells us that the sine of, let's call it theta, I'm going to say, let's write it up here, theta equals arctan of 3/4. So sine of theta is equal to 3/5, and cosine of theta is equal to 4/5. So we can go ahead and figure this one out, can't we? All right, well, we got all that on our own. And we're going to use, yes, we wanted to find out what the sine of twice this would be. Easy enough, huh? So the sine of twice this is going to be 2 times the sine of the single angle, and I have the single angle stuff, 3/5. And the cosine will be 4/5. So we end up with 2 times 12, 24/25. So the sine of double this angle is equal to, let's make sure I got it right, that I didn't introduce some foolish error. Good. Whoops. Can't make a smile unless I've got the pen in my hand. Okay. Use an identity to evaluate this one. And what have we got here? We've got two angles being added together. Arctan 12/5. So I know that for this first angle, so I'm going to say alpha equals arctan 12/5, and beta equals arc cosine, of 12/13. Okay. So I know that my x is equal to 5 for this one. My y is equal to 12. And then because I recognize this as part of a Pythagorean triplet, I know that my r is equal to 13. For this one, I know that my r is equal to 13. My x is equal to 12. My y is equal to 5, and my r is equal to 13. So what I do know about these is that they are complementary. When I add arctan 12/5 and arc cosine 12/13, I'm going to have 90 degrees. So I'm looking for the sine of 90 degrees. Well, I happen to know what the sine of 90 degrees is. It should be, so what I expect this to be is 1. That's what I expect. Let's see what happens. So I can figure out my sine and my cosine for each of these, which allows me then to go ahead and use a double angle identity. So what will this be? The sine of alpha is 12/13. The cosine of beta is 12/13 plus the cosine of alpha, which is 5/13, and the sine of beta, which is 5/13. Now, we expect this, don't we, when we've got complementary angles? Remember, this is the cofunction. The cosine of alpha and the sine of beta are going to be identical. We see that here. So we end up with 144 over 169 plus 25 over 169, which is 169 over 169, which is equal to what we knew it had to be equal to, 1. How do you like that? And then we'll just confirm here. Beautiful. What a nice little example. Rewrite this expression using a double angle identity. Rewrite the expression using a double angle identity. Well, first of all, I'm going to do some algebra. I recognize here, and I hope you do too, that we've got conjugates. When you multiply conjugates together, what do you get? Remember this? A plus B times A minus B will always give you A square, your first one, minus B square. So my first one is sine, so it'll be sine squared minus cosine squared. That's strikingly familiar to me. Didn't we have cosine 2 theta was equal to cosine single theta squared minus sine single theta squared. So this is very similar. What would I need to do in order to get this? Well, as long as I do the same thing to both sides, and this is what I'm thinking of doing, I'm going to multiply both sides by -1. And when I do that, I get a negative cosine squared and a positive sine square. Negative cosine square, positive sine square. It's exactly what I want. I'm going to write it with my positive first. And what have I got here? Negative cosine double theta. Double angle identity. So all of this is equal to negative cosine 2 theta. Looking good? I think so. Use a fundamental identity to write this expression as one term. It's currently 2 terms. Well, oh my goodness. Don't we know, I mean, forget about this for a moment. Don't we know that if we square the sine of an angle and add that to the squared cosine of an angle, that it's going to equal 1? Don't we know that? Sine squared theta plus cosine squared theta equals 1. All I'm going to do here is say theta equals 8x. Therefore, this does equal 1. Oh, these are going so fast. I love them. There's the homework. Problems 7 through 10.